Hello everyone. For those who do not know me, my name is Riley Gray. And today we are talking to you about our experiment H/E. The purpose of this experiment was to investigate Albert Einstein's equation describing the quantum theory of the photoelectric effect and precisely determine the ratio of H/E. H, as we know, being Planck's constant, is about roughly 6.62 times 10 to the negative 34th. E, the charge of an electron, is about 1.6 times 10 to the negative 19th. With this being said, we expect a ratio of about 4.14 times 10 to the negative 15th. The photoelectric effect, in kind of a brief summary, describes the energy required to eject a photon from the surface of a certain material, which is pictured here. The ratio, which I just had mentioned, can be found simply in a graph, which you will see here, and we will also talk about in a little bit. The purpose of our experiment, in addition to this, was to add green and yellow filters to the refracted light that we were measuring to try to isolate the green and yellow wavelengths to see if these filters would have any effect on improving our data. In terms of theory, we're going to go ahead and start off by mentioning German scientist Max Planck, as I'm sure many of you are well aware of. In 1894, he was kind of in charge of investigating blackbody radiation, and in doing so, he discovered that energy of photons came in multiple integers. These multiple integers were all based around a constant, which we now today know as Planck's constant. He was also very famous for the quantum theory of light, which actually won him the Nobel Prize in 1918. The quantum theory of light, which we can see here, is described, as we know, as the energy equals Planck's constant times the frequency of that wave. In addition to Planck's theory, we also need to mention Albert Einstein, the German-born physicist and theorist that we are all very aware of. 3 years after Planck, he won the Nobel Prize for the photoelectric effect. The photoelectric effect, like I mentioned earlier, is that energy needed to eject an electron from the surface of a material. His equation depicts that energy that is equal to the maximum kinetic energy plus that energy needed to propel it forward. So why do I mention those two? I mention those two because our theory of this experiment actually kind of uses a combination of both of the theories, the quantum theory of light and the photoelectric effect. In doing so, you have equation up here, HV equals VE, which is actually stopping potential, which is equal to the kinetic energy plus that energy required to eject the photon. So setting those two equal and doing some rearranging provides this linear equation that we were able to use for our experiment. In terms of this linear equation, you can see it graphed here, where the y-axis is determined by the stopping potential, which I will mention in a little bit how we got to that, and then the x-axis is the frequency of the light we are observing. And then the slope, obviously, is kind of the main focus of this experiment for us, which was H/E. So in terms of what we did in this experiment, you can see a nice picture here that involves all of our equipment. We started with a mercury vapor light source, which is all the way on the far left, and that was then positioned next to a prism apparatus, which was kind of collected with some foam pieces to try to prevent any excess light from escaping. We wanted as much of the light into that columnator arm as we could. On that arm, there's also a little slit, which kind of adjusted for maintaining the amount of light that was coming in and out of the prism apparatus. Through that prism apparatus, you can't see, but kind of the center in there is where the glass prism was, and that is what refracted the light through the telescope arm. The telescope arm also had an adjustable piece that we could move back and forth to kind of focus our light where we wanted it to be. through that arm, the light came out and approached the detector here. Our job was to position the detector in such a way where we could get the certain light we were trying to observe in through the window. This was very difficult for us at first because we weren't quite sure where to position this detector. So we actually began with it pretty far away, thinking we wanted to be able to get as much room as we could to kind of figure out, all right, this is how much light we need in there. If it's further away, we can see and make sure we're not getting any other color light in. And in doing that, we actually found out that we had a pretty high error. So we recognized that there's probably some issues there in terms of it was tough to figure out what the actual stopping potential was too. It didn't stabilize very well. So after a few trials doing it that way, we actually threw the detector up really close, just about as close as you see in this picture, to the prism apparatus to really get a nice concentrated amount of light of every frequency. So in doing so, when we position these slits of light, which you see pictured nicely here, you try to get them onto the detector window as close as possible to that width. You want the maximum amount of light to enter the detector as possible to get an accurate reading. So in doing so, we brought it pretty close to here, and not only then, but we also had to position the detector in such a way as to get that light passing through the window to also hit the actual sensor in the detector. So that was kind of a struggle as well, but something that we learned as we went through how to do that the most effectively. So in terms of the procedure, I kind of mentioned a lot of it right there, but we took measurements for the stopping potential for each frequency of light. So we started with yellow, we positioned it on the window, we zeroed the detector, and then observed the potential change over a matter of minutes. When we did the first few trials, it dropped a ton over 6 minutes and was still not stabilizing very well. When we did it much closer, we were able to get a pretty good number by about 4 to 6 minutes. That actually provided some really nice results for us, as I said. So we did that with each frequency of light, and then we graphed them, which Clayton will talk about here in a little bit, in order to find that slope value. In terms of what we were able to do with the addition of the filters, we threw a yellow and a green filter on, one at a time, onto this area here to help us really isolate, like I said, what type of frequency of wave we were looking for. So in terms of the green filter, we were measuring the green wavelength. In terms of the yellow wavelength.